Welcome, everyone, to the March chapter meeting of the San Fernando Valley chapter of the Climate Reality Project. We're so glad you're here tonight. These are some dark times out there in the world, but nothing makes us feel better than being together in community, learning and working together to make the world a better place. So that is what our meetings are all about. Before we dive in, we like to begin with a land acknowledgement. And sharing our land acknowledgement tonight is Cheryl Cuneo, who is a co-chair of our legislative committee. She took the virtual climate reality training during the COVID lockdown, same as I did actually. But she's a retired costumer, unlike me. I have no particular sewing skills. She took part in multiple quilt projects. She's created an endangered species quilt for the Center of Biological Diversity that's incredibly beautiful. If you ever see photos, maybe she'll share a link to her website in the chat afterward. But she works on the legislative committee with Kathy, and she says that forces her to use the other half of her brain. Cheryl, will you go ahead and share the land acknowledgement for us?
A land acknowledgement is a formal statement that recognizes and respects Indigenous peoples as stewards of this land and the enduring relationship that exists between Indigenous peoples and their traditional territories. It acknowledges the history that has brought us to reside on this land, the colonialism that is present in our current systems, and calls on us to be mindful of our own present participation in it. We acknowledge that we are on the traditional territory of the Tongva, Kizh, Tataviam, and Chumash tribes. I live in Los Feliz, and I don't know if anybody else has been down there, but if you go down to the Ferndale, and right at the mouth of Ferndale is a historic, it is just LA Historic Monument number 112, a Gabrielino Indian site. It's the site of a Tongva village.
And it's wonderful to have such a reminder so close to home, right, Cheryl?
Yes.
All right. Well, at this point, we've got a good crowd, and I think it's about time to turn things over to our guest speaker. I will ask you all to hold your questions for the end. There will be an opportunity to enter questions in the chat after the presentation, and we'll get through just as many as we can before we run out of time. But we're very fortunate to have Dr. Daniel Swain with us tonight. He has been doing this for 20 years, sharing, climate news in a relatable way, a straightforward way. You may have heard him on, NPR, on the BBC, wherever you get your news. You've probably seen a quote for him because he's kind of the go-to guy now when disaster strikes, for his wonderful ability to explain to us all why it's happening. So without further ado, I do encourage you to follow him on his Weather West blog or his social media channels, Weather West. But if you are inspired by this meeting, I suspect you'll want to hear more from him in the future. Daniel, go ahead.
All right. Well, thank you for that. And thanks for the invitation to speak to the group this evening. It is, as you mentioned, kind of remarkable that we are headed into what will probably be the hottest March week ever observed in Southern California, with temperatures in the San Fernando Valley well into the 90s and possibly, depending on how things go, possibly the earliest 100-degree day that's occurred in recorded human history in this part of the world. So it's a bit of an inauspicious milestone, I suppose, but it does seem fitting to have the conversation. And so thanks again for I know we didn't plan that, of course, but here we are. So I do want to talk about extreme weather and climate change. And let me just actually, I almost forgot to share my screen here. So here we go. Just give me a moment. You'll see some weird stuff in the background now. Should see it full screen. We're ready to go. Let's get my cursor in the right spot on the screen. All right. Well, as I mentioned, this evening I'm going to be talking about weather and water extremes in warming California. And, we've seen a pretty dramatic fashion, water extremes on both ends of the spectrum in Southern California multiple times in recent years. In fact, really even multiple times just this season. LA County, on the whole, as was the case for Ventura, Santa Barbara, and Kern counties too, experienced its wettest start to any water year on record this year. Believe it or not, October through December were the wettest October through December months ever observed in over a century and a third of record keeping in Southern California. Since then, though, it's been really dry, and it's also been the warmest, both start to winter and winter to date. And now we're not in winter, really the warmest October through, I guess we'll call it early March period on record, also. So, unlike some recent years, which were extremely dry, this year was both extremely wet and record warm. In fact, record wet and record warm in coastal Southern California specifically. It's a lot to take in, especially following what we've seen in recent years with other swings between extreme wet and extreme dry. We've seen the two worst droughts on record in Southern California within the past 15 years, as well as some of the wettest conditions on record, certainly the hottest conditions on record, as well as the most destructive wildfires on record in between, sandwiched in between even a very wet period from 2013 to 2024, a record dry period thereafter, and now back to record wet just this past winter, and back to very dry and record warm even as we speak. So it really has been a roller coaster that keeps having a new peak and a new fall almost every time I give a talk like this. It's really become quite remarkable. So let me back up a little bit though and take a look at the big picture, literally the big picture here with the global climate context. We know the planet is warming. That's probably a surprise to no one in this group. But it is worth emphasizing. I replace this plot every year. By the way, if for some reason you're seeing this toolbar in the middle of the screen on your end, let me know. Otherwise, I'll just assume it's me. Um, the it's always useful to update this global map as I do each season. This is the most recent version as of January 2026 from NASA. NASA is quietly still producing these maps in the background. Just they're just not getting publicized. So I encourage you to check them out. But really, it doesn't show anything tremendously surprising. And of course, as you'd expect, this map of warming thus far doesn't change dramatically from year to year because it's warming that's accruing over time. So now we've got over a century of warming. The map doesn't change that much from year to year, but it has gotten redder. It has gotten more dramatic with each passing decade. And what we can see now is that the Earth on average has warmed something like 1.3, 1.4 degrees Celsius. That's about 2.5 to 3 degrees Fahrenheit as of 2022. But the last couple of years have been considerably warmer. You may have heard the news, we've stair-stepped upward a bit even faster than we had previously, and the Earth has been at or above about 1.5 degrees Celsius the last couple of years. So the other thing I always like to point out is that the spatial pattern of warming we see on Earth is not uniform. It's not the same everywhere. And in fact, there are some coherent spatial patterns of change that are worth noting. The first of which is that pretty much all of the continents, really any area where significant numbers of humans actually live on Earth, are warming faster than the oceans, which leads to the conclusion that all populated areas are actually warming much faster than the global average. So we hear about 1.5 degrees, for example, of global mean warming, but 1.5 degrees of global mean warming actually means 2 to 2.5 degrees of warming over the continents where people actually live. So the continents are warming about 50% faster than the global average by virtue of the oceans taking longer to heat up because they have a lot of thermal inertia. The other pattern that we see is that the Arctic is warming faster than anywhere else on Earth. In fact, by a factor of 3 to 4. So the Arctic is warming 3 to 400% as fast as the global average. And this is why we're so worried about loss of polar sea ice and the polar ice sheets, particularly in Greenland and Antarctica. So we see these two patterns. We see the continents are warming faster than the oceans. We see the Arctic is warming faster than anywhere else. It turns out that that spatial pattern is also a fingerprint of human-caused warming. It is one of several key physical reasons why we know that the warming we've observed is in fact caused by the increased concentration of greenhouse gases. Other causes of potential climate warming would look different than the one we're actually seeing. So what is causing the warming? Again, I think this is probably just a quick review for everybody in the group, but we know that the accumulation of heat-trapping gases in the Earth's atmosphere, known as greenhouse gases, essentially amplifies the erstwhile natural greenhouse effect, which we do want. We don't want there to be no greenhouse effect, or we'd live on a planet that was mostly frozen over with ice, including all the way down nearly to the equator. The Earth has done that in the Earth's history previously, and we're lucky not to live in that epoch of climate history, but we're living through a completely different but increasingly tumultuous epoch of Earth's climate history as well, because that accumulation of greenhouse gases caused by human activities includes most obviously fossil fuel burning, so think about tailpipe and factory emissions, but also agricultural activities and land use change, so urbanization, the conversion of forests and grasslands to cropland, things like that actually are a more than trivial contributor. About 20 or 30% of the total warming actually does come from land use change as opposed to fossil fuel burning, so it's a significant piece of the total. But for perspective, carbon dioxide levels at this point, circa 2025, are now the highest in at least 800,000 years. So think about what was going on Earth 800,000 years ago. It certainly, in terms of humans, nothing that resembles the modern world today. And where are we headed? Well, we have made lots of progress in green energy. In many parts of the world, the cheapest form of new electricity generation is indeed wind, solar, or something else that doesn't have large negative externalities of carbon emissions. But on the other hand, that's only one part of the puzzle. And unfortunately, we really have not bent the top line carbon curve as significantly as we would need to really move the needle on global warming. We still have rapidly increasing emissions. In fact, 2025 top line carbon emissions were a new record high. So not only are the concentrations of greenhouse gases continuously increasing, which you can see illustrated here from these plots from my colleague Zach Labe, but the actual climate warming potential of those emissions over time is also increasing year on year. So that's the curve that we ultimately need to bend, and it hasn't happened yet. So we are currently on a path toward more than doubling the present day warming. So we've seen about we're getting close to 1.5. We're on a path from about 2 to 2.5 to 3 or so on our realistic trajectory. I mean, it's pretty uncertain because it includes both the geophysical uncertainties and the geopolitical ones, which I think, as is illustrated quite profoundly this month of all months, the geopolitical ones are just as large, if not larger, than the geophysical ones in terms of what's going to happen next in terms of global carbon emissions and the carbon economy. Uh, and the reason I mention this is not just to scare everybody, but is to make one really important point, which is that yes, we absolutely need to reduce and eventually effectively zero out our carbon emissions to actually solve the underlying problem of warming. That's absolutely true. It's urgent work. We have to do it. We're not doing it nearly fast enough. But the other thing we got to do in the meantime is think about how we can better adapt to the large changes that are already underway and that we know are going to get larger before we can stop this train. We really do have to be doing both. And I think we've sometimes lost sight of the need to adapt at the same time that we mitigate. So we need to be able to walk and chew gum so we can solve the underlying problem and not suffer untoward consequences along the way. As we work to actually solve the underlying problem, we have to also work to mitigate its consequences. So where are we now? Well, I like to localize in these presentations to a specific place, and LA County has been warming quite rapidly in recent decades, and you can actually see that LA County has, of course, been warming since the late 1800s, but the rate of warming really started to pick up after the 1970s and the 1980s. And interestingly, sometimes people will say, "Ah, that's just the urban heat island effect taking place." But if you think about it, when did most of the urban and suburban growth in Los Angeles County occur? And it was not after the year 1990. A lot of that suburban growth and sprawl had already taken place by that point. So, not that we have any real question as to why this is happening, but it's an interesting reflection that a lot of the warming that has occurred really has occurred in my relatively short lifetime, but certainly since the 1970s. And this is something where we've kind of stair-stepped upward, where even though we've had a couple of years recently that were cooler than the recent peak around 2016, 2017, even the cooler years in the last decade are actually would have been nearly record warm years 50 or 60 years ago, which is kind of a shocking perspective here. All of California's warmest years on record then have occurred in the last decade, and none of its coolest in the last 15 years. So that's a classic sign of a non-stationary warming climate. And in California more broadly, we've actually seen even more rapid increase of summertime maximum temperatures. So really think about this as the typical summertime heat wave. How much has it warmed up? And the answer is, well, quite a lot. And the rate of summertime maximum temperature warming is greater than the warming in other times of year. So it is the hottest hots getting hotter faster than anything else. And to the point that all of California's top hottest summers on record have occurred in the last 10 years. And this does include even some of the winters that haven't been particularly warm. Now, 2025, 2026 is not one of those. We've now just experienced the warmest winter in Southern California history by a considerable margin. So, once these plots get updated for 2026, we're going to have another record warm year. But especially, again, notice this really rapid warming we've seen again since the late 1970s, early 1980s, where we really are living in a different climate than we were in California just 4 or 5 decades ago. But the rest of this talk, I actually want to move beyond temperature because it's actually more, or I guess it's less intuitive and even more important in some ways. And here I'd like to introduce the expanding atmospheric sponge effect. This is a, a term or an analogy that my colleagues and I coined in a paper last year to kind of articulate in a hopefully tangible, visible sense why warming air temperatures matter so much for hydroclimate, for rain and snow and evaporation and things like that, and therefore for drought and flood and wildfire. As temperatures rise, the analogy goes like this. The water vapor holding capacity of the air itself rises rapidly. For those mathematicians in the room, exponentially. It is literally an exponential function. Not figuratively exponential, but mathematically so. And it acts increasingly like an expanding sponge that expands at an exponential rate. In fact, that rate is approximately 4% per degree Fahrenheit or 7% per degree Celsius of warming. So it's a modest but not tiny amount for each degree of warming. Once you get to several degrees of warming, you can see how this actually starts to become a pretty significant factor and is also compounding. Literally, if you could have 4 or even 7 or even 4% compound interest in a savings account or something, I think most people would be thrilled with that these days. But when it comes to compounding water vapor or the water vapor deficit on the other side of things in the atmosphere, this can become a bit of a problem. But the way I think this analogy makes the most sense is to just imagine, well, this expanding ordinary kitchen sponge sitting on your kitchen counter. Imagine it's ordinary size one moment and then it's comically oversized the next. And imagine you spill a glass of water on your counter or something small. The small sponge can probably soak up that glass of water, but just barely. It's going to be completely saturated. And you're going to wring it out over the sink, and you'll yield about as much water as it absorbed in the first place. That larger sponge is going to soak up all of that water and still have room capacity inside of it to soak up even more. So say it's the comically oversized sponge and you spill a whole pitcher of water on the counter. Well, now your comically oversized sponge is going to be able to absorb all of that. You wring that out over the kitchen sink and it's going to yield, well, a pitcher's worth of water instead of a glass. So they're both sponges, they're both an identical material, but one of them had a much greater capacity to absorb the water and when wrung out yielded a lot more water. And that's analogous to increasingly intense precipitation by virtue of the Earth's expanded or increased capacity to hold water vapor. But the interesting thing about this analogy is that it also works in reverse. The caveats apply to a metaphor which is kind of unusual. If there is no water, if you spill nothing on your kitchen counter and you just have your ordinary and then your comically oversized sponge, they both contain exactly the same amount of water in them. 0. And this becomes important because what it means is that an unsaturated but larger sponge has a greater capacity to absorb water, but isn't actually absorbing more water if that water isn't available. And this becomes really important in understanding things like drought and wildfire conditions in a warming climate, because on the one hand, the expanded atmospheric sponge, when it is saturated, when it's wet, when you're in a cloud, when there's already precipitation occurring, is just that much bigger, and you get wetter wets. Think about the really wet fall and early start to winter we saw this year, record wet in Southern California. But then, when it is not wet, when it is in fact dry, which is more often the case, statistically, more days in Los Angeles are dry than wet in a given calendar year, that expanded sponge actually leads to greater rates of evaporation. It wants to draw more moisture out of the landscape, desiccating it. And so, essentially, the net effect is that you increase the ceiling on both how intense precipitation can become on the one hand and how intense evaporation can become on the other. So, water going up and water coming down both accelerate. And what this leads is to an increase in the risk of flood events as well as an increase in the risk of drought events, and in different of the different transition periods between the two, increased risk of wildfire events. And I'll get to that in a minute. And we actually think that from recent science conducted in the last few years, that this is a pretty widespread process. Don't worry too much about the numbers here, but the point is, anywhere where you see purple on planet Earth is where there is a significant projected increase in overall top-line hydroclimate whiplash. These swings between wet and dry, driven largely by this expanding atmospheric sponge effect. And what you can see essentially is that, yes, the magnitude varies from place to place, but in general, it increases everywhere or almost everywhere where people actually live on planet Earth. So over almost all the continents, with only a few isolated subtropical ocean regions seeing a decrease. So this is going to be a pretty universal human experience across climates, Mediterranean, tropical, Arctic, and otherwise, in a warming climate. So why do we care? Well, in Southern California, this is becoming an increasingly exercise in repetition, just because everybody's lived it. But just to emphasize one reason, one very dramatic example, back in late 2017 or early 2018, it's not that this is the worst fire that we've had since then. This has since been eclipsed many, many times by subsequent fires, but it really is an interesting illustration of how we went from a very serious, destructive wildfire immediately into rainy season just a few weeks later, with catastrophic flash floods and debris flows that killed quite a few people in Santa Barbara County and destroyed a lot of homes, when a very heavy downpour fell right over the recent burn area that was even still smoldering. It was a 1-2 punch. Both of these were catastrophes in their own right, and together it was really devastating for Ventura and Santa Barbara counties. But if we characterize this mathematically without being clever about it, on average it would have been considered mostly sunny and breezy with below average precipitation between December and January 2017-2018. So my point here is this is just a really helpful illustration of why, if we only consider average changes in climate, we're often just going to completely miss the point. And this might sound obvious, but often when I talk with people who are working to adapt to a changing climate, that's exactly what these analyses have presumed. They've looked at the average, they've looked at the change in the average annual precipitation, which, as I'll show you in a moment, is potentially a very problematic assumption. So what is going on in California? Well, we don't really see a large trend in annual average precipitation to that point, despite the fact that we've seen a large increase in drought frequency and severity. And so you might ask, well, what gives? And the answer is that there has been a significant increase in the variability of hydroclimate, in the propensity of the landscape to experience large or frequent swings between wet and dry. That still doesn't explain exactly why, but it starts to get to the math of how this can balance out. And we have any number of just visceral examples from different parts of California. This is from Northern California now, where we've just swung wildly back and forth between one extreme and the next. California does have a naturally variable hydroclimate cycle throughout the calendar year. We have wet winters, we have dry summers, which is what you can see in this animation here. And that's a pretty reliable pattern, and to a first order, we don't really expect that to change in a warming climate. So that's one thing that, if you like it, that's great. You're going to keep getting it. If you were hoping it was going to change, I'm sorry to inform you, we're still going to have the same seasonal cycle. But the reason I bring this up in this context is that it does predispose California to a certain background level of whiplash that doesn't have to do with climate change, but it's just a fact of life and of living in this variable part of the world. Because we only really get meaningful precipitation, especially in coastal Southern California during the winter, it means you really only have about a 3 or 4 month window any given year to really stack up whatever water you're going to get for that whole year. If it doesn't really rain in the winter, you're out of luck in California until at least the next winter. You're at the mercy of the following winter, and it's easier to fall into a drought that way, as opposed to another location, which in many parts of the world you have more than one rainy season per year, or the rainy season is also the warm season. But in California, it's generally not raining when we need the water, and it's raining a lot when we don't need it as much in the middle of the winter. So it's almost perfectly out of sync with temperatures, and this is a globally unusual pattern, which leaves us susceptible both to drought, but also to flood, because what it means is that much of California is not a desert and actually gets quite a bit of water every year to support its rainforests along the north coast or the coniferous forests, even in the mountains of Southern California, certainly in the Sierra Nevada. What that means, though, is that because we've really only got one chunk of the year rainy season, all of that water, which is considerable, has to fall all at once over a few months. And sometimes we get too much of a good thing and we have a flood problem in winter, thanks to the fact that the geology is essentially shaped by these occasional very large storms and a prolonged dry spell essentially every year. So this high background degree of whiplash from season to season. Interestingly, climate models, the predictive tools we use to peer into the future, suggest a significant increase in the wettest wet, so in the wettest years, a significant increase also in the driest dry years, especially in Southern California, where you notice there's perfect overlap in Southern California between large increases in the wettest wets and large increases in the driest dries. And another quantity that is maximized right across coastal Southern California, an increase in the swinginess or the whiplash between wet and dries. The fascinating thing about this is that the very same climate models here suggest that the average annual precipitation in this part of the world might not change very much, which is striking when we see that in fact it has not changed very much, but that there is early evidence of increased swings between extreme wet and extreme dry. We also see this potential for this to play out at the seasonal scale, where yes, we still have wet winters, yes, we still have dry summers, but where in fact we might even see greater accentuation between those two. So with drier shoulder seasons, drier autumn, drier spring, but an even wetter winter. So an even more winner takes all type situation in winter that leaves us more exposed to floods when it is raining, more intensely in the wet season, but also more exposed to droughts and fires the rest of the calendar year, which is not exactly what we'd like to see, but we're certainly seeing that play out in recent years. On the flood and the wet side of things, the main mechanism for this is an increase in the intensity of what are known as atmospheric river storms in California. These are plumes of highly concentrated water vapor moving fairly rapidly in the air above your head. These are the classic winter storms. LA has seen more than a few big ones in recent years. You may have noticed the flooding in the LA basin multiple occasions, both this winter and last winter, especially earlier in the season. But these atmospheric rivers are both a blessing and a curse. If we didn't have any of them, we would not have enough water for California to survive and thrive as it has historically. But in the context of future climate change, we know that these atmospheric rivers are likely to become more intense and pose an increasing risk of flooding because of that expanding atmospheric sponge. Well, the wet side, it's mainly amping up the most extreme atmospheric rivers in this part of the world. California does have a major history of severe flooding, and that does include LA County. It's the reason why LA River and other rivers in LA County and Orange County are largely in concrete boxes for much of their path out toward the sea in this modern era. They did not used to be, and LA used to flood quite frequently and severely. We know now there are significant environmental costs to having rivers in concrete boxes, but it is a bit of a trade-off because it is in fact the case that those rivers in those concrete boxes used to cause destructive floods in LA every couple of decades, and we haven't seen one since. But as I mentioned, there are trade-offs and there are questions too about whether that really would be adequate in a sufficiently large climate change supercharged flood? Would that even be enough to protect LA from the largest floods of the future? Well, we do know that California is susceptible to really big flood events that exceed anything we've seen in California's modern era every 1 to 200 years. It is pretty obvious that a modern day repeat could be a real disaster, and it's but considered by some to be California's other big one, the original big one being, as you probably have all heard, the large magnitude earthquake on the San Andreas Fault somewhere in the LA basin or up by San Francisco. Uh, and we believe that climate change has already approximately doubled the likelihood of an event like this occurring quietly in the background with the amount of warming we had as of a couple of years ago. While everyone was so preoccupied with drought and wildfire, for understandable reasons, they really had accelerated and we really were grappling with the consequences. But the reason I bring this up is it's people sometimes feel like it's out of sight and out of mind. But the challenge with this is that, of course, I'm much more concerned about the things we don't see coming than the things that we do. The things that we see coming, we can mitigate, we can adapt to and reduce the harms associated with those events. But it's never good to be blindsided. And there is a real risk of that happening with the risk of a severe flood event in California because we do believe there's about a 2 in 3 chance of a modern recurrence of an event we haven't seen the likes of in over a century. And this is partly because over any given 40-year period, the odds are not trivial, even without climate change. But now, over the next 40 years, as we see continued increases in greenhouse gases and further warming, further increase in the size of that figurative atmospheric sponge, that really is going to up the ante. So we know that the same amount of rain and snow simply doesn't go as far as it used to. We're seeing the effect of this quite dramatically play out this winter amid record warmth and record low snowpack in many places. This isn't necessarily because precipitation is declining on average, but it's because we're having more dry days in between that rain and snow, and therefore more evaporation occurring in between storms. There is less snowpack, as we've seen this year, and shorter snow seasons, which we're certainly seeing this year. You can kind of boil this down to the fact that droughts, historically, they used to be hot or cold. You could have a low precipitation period and it could be warmer than average, or you could have a low precipitation period and it could be colder than average. But circa 2026, all droughts are hot droughts now because it's pretty much just warmer than average 100% of the time. So you can blame the dry side of the expanding atmospheric sponge essentially for increasing drought frequency and severity. No decrease in precipitation, at least on average, is even needed for that to be occurring. And so when some folks will say, look, California's precipitation hasn't decreased, aha, there can't be any climate change effect on drought in this part of the world, you can tell them, have you considered the expanding atmospheric sponge? This leads us to kind of a challenging place where the very most intense rainfall is what's increasing the most, but the more beneficial or benign, light to moderate events are probably going to decrease and go away. So we're left with the most extreme downpours, which become even more extreme, and we lose the gentle showers. This, combined with the driest side of the expanding atmospheric sponge, means there's greater soil drying amid less frequent precipitation events. The air is literally thirstier in this setting, with the net result being less frequent but more severe floods. Now, this is a challenge because what it means is that the floods that we observe most frequently, the small to moderate sized ones, are the ones that probably aren't going to increase noticeably because of the countervailing effect of the increasing atmospheric sponge. But on the other hand, it tells us that the very most extreme floods, the ones that cause the biggest problems but occur the most rarely, and therefore the ones that we don't observe very often, again, out of sight and out of mind, are precisely the ones that we should expect to increase the most. So that leads to a really difficult challenge in communication and climate adaptation. How do we effectively convince decision makers and water managers and flood control folks to really understand this fairly nuanced concept that what's happening with average precipitation, or even what's happening with the relatively more ordinary floods, the magnitudes you might get every 5 or 10 years or something, could be completely the opposite of what's happening with the very most intense events that occur historically, maybe once in a century or so, but in our lifetime with climate change might be occurring every several decades. All of this leads me to wildfire because it's pretty clear that we have a problem with increasingly destructive wildfires, California and beyond. This is an audience in LA, so I don't really need to explain what that means to anybody, but we already see a more than doubling in the frequency of extreme fire weather conditions, especially during autumn. I'll show you winter in a moment. That's relevant to the LA fires last year. But essentially, the reason for this is we have drier vegetation over a longer and hotter fire season, which increases the rate of spread, the actual thermal intensity, so literally how hot these fires burn, and maybe most importantly, their behavior, the extremity of fire behavior, and therefore their potential destructiveness. It's a real challenge. And this is probably one of the most talked about aspects of increasing hydroclimate whiplash over the past year or so. So I'll run through it to just really drill down a bit. We had an exceptionally wet period, if you recall, from winter 2023 into 2024. So winter 2023 and into spring 2024, that 2 year period was one of the two wettest 2 year periods on record for much of Southern California. The UCLA Climate Station, I believe, had its second wettest 2 year period on record. So not quite record breaking, but right up there at the top. Extremely wet. And there was, as a result, uh, a, a period of very abundant herbaceous vegetation growth, meaning essentially grass and shrubs. Um, but then we had a summer that across the interior of Southern California was the hottest on record. Not so much in the coastal zone. It was actually a little bit chilly in LA proper. But then everywhere in Southern California, coast, valleys, mountains, wherever, deserts, experienced a record dry start to the water year in 2024. So beginning in September, October, it didn't rain. It still didn't rain in November, still didn't rain in December, and then we got to early January and it still hadn't rained at all in Southern California so far that season, following a 2 year period of extreme fuel buildup with highly abundant herbaceous vegetation accumulation, essentially doubling the typical grass biomass leading up to December. And then, of course, we had an extreme offshore wind event amid record dry vegetation conditions in early January 2025, and we know what happened next with the devastating fires in LA. But I've just added yet another arrow to this slide, going back in the opposite direction because we just swung back in Southern California, October through December, the wettest such period on record, even beating out the 2023-2024 period before it. And so we've swung the pendulum back from very wet to record dry to very wet, and as we speak, with a record warm March in the cards and 95 plus degree heat for much of the coming week in Southern California, we may already be swinging yet again back in the other direction. And the reason why this matters so much is that I was grateful to have the excuse to create a slide like this year, not because it's good news, but because I think it's helpful in articulating really what's going on here. In grassland ecosystems, and this extends to woody shrubland like chaparral as well, which is prevalent, of course, in coastal Southern California, the most active fire periods often follow, historically at least, some of the wetter periods because you have periods of fuel accumulation. There's literally more growth of vegetation during the wet periods or following the wet periods than there is during big drought periods. You just don't have as much grass and shrub growth when it is bone dry. You can, if you've ever mowed a lawn, a well-watered one versus a non-well-watered one, I suspect many of people in a climate reality group in Southern California probably don't have as many lawns as the general population anymore, but I do still think most people understand the link to a well-watered lawn versus a desiccated one. But the well water one grows more, and then if you let it, if you turn off the irrigation, it's going to dry out completely, and you're left with dry brown grass. And that's what happens in the natural world as well. We see that these fuel accumulation followed by desiccation cycles, so particularly when we have really wet conditions followed by anomalously hot and dry conditions, are in many ways the quote unquote worst climate for wildfire in grass and shrub ecosystems specifically. They predispose to having higher intensity, higher frequency fires as opposed to it just being hot and dry all the time, where you have an initial spike in fire activity and then it dies down because you start to run out of fuel. This is exactly what we've experienced recently, repeatedly, and it's what we expect to see more of in a warming climate. And it is worth noting that this is different than how forest fire risk works. That one is a little more intuitive. Essentially, the drier it is, the greater the risk of forest fires, the greater the intensity of forest fires. Because if you think about it, trees in a forest, they aren't really growing or dying back dramatically year to year, whether it's wet or dry. Grass very much will grow or not grow abundantly in a given year, and you can actually see visible differences many times in your lifetime, even many times within a decade. If you go out into a grassland following a really wet year versus a really dry one, you go into a forest though, and you don't see as much variability from year to year. Here, it really is the driest periods that predispose to the highest risk fire conditions, which then means that we're actually seeing more of both in a warming climate because, of course, we are seeing drier dries and worse droughts. That does increase forest fire risk, and there's lots of research on that. But this emerging paradigm that the fuel accumulation to desiccation cycles brought about by increasing wet to dry hydroclimate whiplash. It's maybe not new to folks who work in the ecology world, but it is a relatively new paradigm in terms of people actually thinking about wildfire risk at scale. And I think the recent experience in Southern California is a big part of the reason why that's being more seriously considered. And when we look at the extremity of fire weather conditions in coastal Southern California, we put this out just a month after the fires last year, we do see that even in peak offshore wind season from November to January, so essentially in winter, we do also see, in addition to in summer and fall, an increase, a significant increase by over a third actually since 1980. So this is not small at all in the most extreme fire weather conditions in coastal Southern California. And so clearly we've got a problem, and I've had the misfortune of being able to add a new panel to this slide of destructive wildfires in California every few years for the past decade or so now. Uh, but I do want to emphasize something because I think it's a really important point, which is that wildfire itself is not inherently bad. It is a natural process, and sometimes we forget this. It's really the intersection with populated areas that's become the problem. And we've seen terrible disasters in recent years, and unfortunately, even worse ones are plausible, given the risks that we have today. But I think the burning question is not so much can we decouple fire from the catastrophic effects it's had recently, since it's pretty clear that it is possible. It's really more of a question of will we do it? And that remains a bit of an open question. But I think the optimistic take on this is that it is possible to decouple fire from catastrophe, but will we? And I think that's the tension that exists in California, throughout the West, and really in fire-prone regions all around the world in this difficult moment, reeling from recent fire disasters. So, all right, so let me sum it up so we have some time for questions. What do we expect in a warming California? Deep breath. So much of what you'll experience 10, 20, 30 years from now will be familiar. We're still going to have wet winters, dry summers. It's still going to be warmer in the summer, cooler in the winter, and there'll still be fog most years along the coast, May and June gloom, those kinds of things. It'll still snow sometimes in the mountains, and it'll rain sometimes in the valleys. That will remain familiar, but we'll see increasingly volatile variations on those relatively familiar themes, and we will see years that or individual episodes of extreme weather that feel very, very alien to us. And I would argue that what we're experiencing this winter, essentially, which is on a lot of the American West, it feels an awful lot like a year without a winter in the sense that it has not been very cold. It's been summer-like or spring-like warmth in many places all winter. There is very low snowpack. That this is one of those winters where it feels not so familiar. It really feels anomalous, and the data support that it is. It will be warmer still, of course, with rising water and wildfire whiplash. That's kind of the main uh, statistic of consequence I expect to see in California. And what can we do about this? I think the bottom line, and of course I have much more to say about this in a lengthier conversation on adaptation, but I think the number one thing to think about are interventions that are flexible and proactive, being able to roll with the punches, as they say, because with increasing volatility, we can't just be preparing for one end of the spectrum or the other. We need to prepare for flood and drought simultaneously because if you only focus on drought, if you only focus on wildfire, you leave yourself potentially more vulnerable to flood. But if you are circumspect and think about all of these risks at once and what kinds of interventions are commensurate with addressing all of them in constructive ways, you can actually come out ahead. This does involve things like using fire to fight fire, prescribe burns, the in ecosystems where they are appropriate, re-expanding the paradigm of indigenous and cultural burning going along with that. There's a spectrum from sort of contemporary prescribed fire to cultural burning that achieve partially overlapping objectives, including the reduction in the risk of subsequent unwanted or catastrophic fires. And there's actually a similar thing that we can do with floodplains, floodplain restoration, levee setbacks, thinking about how to allow more water to percolate back into groundwater tables and aquifers. This is easier said than done in some locations, and LA County, of course, is different than, say, San Joaquin County because there's a lot more people, there's a lot more pavement, there's a lot more infrastructure than there is in a place where you primarily have farmland and small towns and highways connecting them. But even in LA County, there are opportunities to do both of these specific things, prescribe fire and improved groundwater recharge. So even though it may be on a smaller scale or more localized, in some ways that means you can do it closer to your own community. And I think that there's a real opportunity to look for opportunities that are co-beneficial, sort of interventions, risk-reducing interventions, climate adaptations that have their own intrinsic benefits, even absent their effect on reducing our vulnerability to climate change. So things that have societal or environmental co-benefits, projects that we like to see in the community anyway, but as a side effect also happen to be designed in a way that reduces the risk of drought or flood or wildfire or some other relevant hazard. So with that, I will close. I'll leave this up on the screen, by the way, for a little while. And you can find me, as was mentioned in the introduction, I'm very online for better or for worse. If you want to pick one place to go, I suggest either the Weather West blog at weatherwest.com or my YouTube channel at Weather West, where I host live weather and climate office hours on a nearly weekly basis as part of my University of California Agricultural and Natural Resources role. In fact, I actually had an hour and a half live stream earlier today, which was recorded, as they always are. If you go there, you can find it, where I talk about the upcoming record-breaking March heat and the broader implications for snowpack and wildfire throughout the American West. So finally, there is on the screen a QR code at the bottom there. If you happen to be so inclined, that's a survey from the University of California regarding my weather and climate communication activities, and we'd always greatly appreciate 3 or 4 minutes of your time if you could fill that out. Helps us make sure we're reaching the broadest possible audience. So thank you again.
Thank you so much, Daniel. That was great. So much to think about in that presentation. And I, for one, am not particularly looking forward to the next few days. I live in Woodland Hills, which is famous for being the hottest part of the valley, hottest part of LA. So, when we had a major heat wave a few years ago, my outdoor thermometer registered 121 degrees, and I'm certainly hoping that we don't break 100 this week in March, but I am bracing for it. All right, everyone who wants to ask a question can go ahead and start entering them in the chat, but I'm going to kick things off with kind of a crazy question because this is something that, people ask me and that comes up a lot. Where do you think is the safest place to live given climate change in the next few decades? People are always saying, like, should I move out of LA? Should I go somewhere else? Where do you think is the safe place?
Yeah, this is the number one question over the past 3 or 4 years that I've received, and I don't think it's an answerable question. Partly because it really just depends what you're most worried about. It's very much a frying pan into fire type of question. Um, you know, One thing you don't really have to deal with in some parts of the world is something that you have to deal with in quite dramatic fashion somewhere else. LA is decidedly sort of a geophysical epicenter of various natural hazard risks. It's an earthquake-prone region, it's a fire-prone region. It is, to many people's surprise, also a very flood-prone region as well. But it's not. Yes, they can occur, but you don't live in Tornado Alley, for example. You're never going to get a blizzard or an ice storm in downtown LA. I'd bet my the rest of my career on that one. But and there are other parts of the country where that's something you'd probably experience on a somewhat regular basis. Just today, there were devastating tornadoes in the upper Midwest, for example, and that's just not really something you have to worry about in LA. On the other hand, you live in Chicago and you don't really have to worry about wildfires. At least not in the city. Although again, even you go up into Wisconsin, you go up into the Upper Peninsula of Michigan, and there's actually more wildfire risk than you might think. Same thing, believe it or not, one of the highest conditional risk places for a really big fire in an unexpected spot in the country. Folks are surprised to hear this, but it's New Jersey or Long Island. And so just goes to show you, sometimes it's the risk you aren't thinking about, and that your community is less consciously preparing for that are actually scarier than the ones that you know are real, but because you are anticipating them, you've actually done some things to reduce the risk, which is the case in LA for wildfire and earthquake. There's a lot more preparedness for earthquakes in LA than there would be in a city that doesn't have that kind of history. So it really depends what you're most worried about and the hazards. And there's been these news stories about climate haven cities over the years, which always make me just very frustrated as a meteorologist and a climate scientist because they almost always highlight some of the highest risk cities as the haven cities, and it's exactly because of that mismatch between expectation of where the risks are and where the most dangerous conditions actually occur. Asheville, North Carolina, for example, was on everyone's list as a climate haven city. And I always thought that was bizarre given the risk of an extremely serious flood there, which people say, oh, well, it hasn't happened in a couple centuries. That does not mean the risk is not very high. It just means it doesn't happen frequently. But we know geographically, geologically, climatologically that if a flood event happens in that part of the country, it's likely to be very, very serious. And we saw what happened a couple of years, I guess it was almost 2 years ago now. So it's a difficult question to answer. People would have said British Columbia, and now British Columbia has been the epicenter of 120-degree heat waves, catastrophic floods, catastrophic fires, catastrophic everything in just a 3 or 4 year period. And I think people have rethought that one, even though, again, this was something that was physically foreseeable. So I think it actually, honestly, I think that it's a question that I would apply more at a local scale. It actually makes more sense to ask that question in the context of a specific area or a specific city. Where should I live within said city? Because within LA, for example, there are places that are at such high risk of wildfire, I couldn't, in good conscience, ever, even spend the night there during fire season. That is how high the risk is. And yet, there are parts of LA that are also at virtually zero risk, like essentially negligible risk of fire. One city, completely different risk profile for exactly the same hazard. And same thing of risk of flooding. You can imagine how that's a good example of how you and even your neighbor might have a really different risk. If the home or the building you live in is 5 or 10 feet higher than your neighbor, one or both of you could be in a completely different situation than the other. And so here, it really does, I think, make sense to think about if I'm worried about floods, I probably shouldn't buy a house on the lower side of the street, or I might not want to move into an apartment in the low spot on the floodplain. I think that's a maybe a more realistic way to think about it and a more actionable thing because more people have flexibility potentially where they live within a given region or a given city than sort of picking a place somewhere on the globe. So I know it's a long answer, but I get that question a lot, and it's maybe not a satisfying answer, but are you afraid of fires? Are you afraid of water, too much or too little? Are you afraid of tornadoes or earthquakes or ice storms or sea level rise? Or the confluence of some of these things? It really just is a question of sort of, it's both personal preference and also geophysical optimization, I guess.
Well, I think it's a good point that, even within a place that has hazards, there are ways to choose a less risky home or neighborhood. I will point out that, we had that really wet winter, 23 to 24. And it turned out my house was not built for that wet a winter. My house grew mold. And I had to, get a third of it down to the studs and rebuild, this time with drainage. So we were fine this winter when the rain comes, but that was a very expensive mistake and not one that I knew to look for when we bought the house because I was young and dumb. But, given that, do you think that when we talk about, like decoupling wildfire from catastrophe, is it really more about home hardening and, zone zero, keeping plants away from your house, as long as you're choosing a location to live that isn't, literally in the highest zone where you would be unable to escape?
Yeah, I think I mean, that is a very big part of it. It is the structure hardening. It is thinking differently about how we manage vegetation in the populated landscape. And I think, it really does depend on the context. And I think that there is, there's a decent chance that some of the very worst wind-driven wildfires under extremely severe drought conditions, they're still going to burn even probably some fraction of the best protected structures that have the best practices in terms of management. On the other hand, every other lesser fire probably wouldn't. And that's where the huge benefits accrue, is under anything but the very most extreme conditions. These interventions are hugely successful in mitigating risk. And of course, that's what you're going to encounter more often than the very most extreme fire weather you've ever experienced. And even under those conditions, there's still benefits. It starts to become a little bit diminishing. But under all the other conditions, they're incredibly useful. And there's also multiplicative benefits. So every home, every hedgerow, every wooden fence that doesn't burn is a source of embers for the next line of houses that doesn't exist. And so, just as having a few houses in the neighborhood go up radically increases the likelihood that the next row of houses goes up, and this is how you start to see these hundreds and even thousands of structures lost. It's almost incomprehensible until you think about the exponential math. It also works in reverse. Every structure that doesn't catch because it was hardened, even if a few of them do, makes it exponentially less likely to become this mass conflagration that we've seen. So there are huge benefits to this. And yes, I think really one of the big things is, given that people live where they live, the neighborhoods are where they are, suburbs are where they are, that is probably the most actionable short-term thing that people can do. Partly because individuals can do it, first of all, and the benefits start to accrue to you personally immediately and then to your neighbors thereafter. And there's neighborhood scale benefits. If all your neighbors do it, then everyone benefits even more than if just a few people did it. Same thing at community level. But it's also thinking about managing landscapes. It's thinking about not being so afraid of prescribed fire in places where it's appropriate. It isn't appropriate everywhere, ecologically, but it is in more landscapes than not in some form. Thinking about, what does it mean to have a beautiful home or neighborhood in a fire-prone place? It probably, if we don't want to keep having disasters, it probably can't mean exactly what it's meant historically. And that's not just true in California. It's true in the Pacific Northwest. It's true in the Rocky Mountains. It's true in the Mediterranean. It's true in Chile. It's true in South Africa. I mean, it looks different. It has to look different if we don't want these to continue. And so, but again, that's something that can be done. And this is, I think it makes it feel a little bit less enormous than the broader problem of climate change, which, you know, is inherently a global problem requiring global solutions. And that, yes, we should start at home, but also our incremental emissions reductions don't immediately improve our risk profile locally. But that's actually not the case for these adaptation measures, where in fact, the more you invest locally, the larger the benefit is immediately and in the same places where you made those investments. And I think that's maybe the strongest argument for it, is that the more you invest in a given place, the more benefit you get in that same specific place in the short term.
The climate reality motto or tagline is local action for global problems. So what you're saying fits right in, right? There's plenty that we can do at the local level that does improve our safety and, the pleasantness of our lives as it gets hotter, um, even if we don't have immediately control of the global issue. My counterpart in the LA chapter has a question about the effects of ocean, um, and specifically the kelp forests that are offshore of LA and how they have affected, the June gloom weather pattern where we get this coastal fog. The theory is that, the loss of the kelp some years ago has been actually contributing to that increase in temperature through the spring and early summer as we lose some of the June gloom. Do you see that pattern? Do you think that those are correlated?
So I'm very far from a kelp ecologist. Uh, Although I did have on my dissertation committee a person who asked me about phytoplankton blooms in the Arctic, so I don't know. Maybe there's more of a connection than one might assume. But I'm neither a biologist nor an oceanographer, so I may not be the best person to answer this. But I think I've actually never heard that before, in any informal or scientific setting. It wouldn't be on my top five list of reasons why. the ocean has warmed as much as it has? The number one reason is unfortunately it's just the atmosphere warms and the ocean warms beneath it, essentially. Um, I'm just trying to think about, I mean, it's interesting. So if I were to test that, I don't think anybody has, to my knowledge, but if I were to test that, what I would probably be looking for is whether the energy absorption by the surface ocean has changed because of changes in the prevalence of the kelp. Kelp is dark in color, and it might affect the amount of sunlight energy, essentially energy from sunlight that's absorbed near the surface of the ocean. I don't know if that's actually the case. I don't know if it's the kelp loss has been on large enough scale to have a large effect. It's an interesting hypothesis. I have absolutely no idea as to whether it's actually occurring. It could be, but I don't think it would be a top, one, two, or three factors to why the warming occurring. It is unfortunately the large scale warming that we're seeing that's transferring to the ocean. That's the main thing. But could it be augmenting it locally and affecting the marine layer? I mean, I think the more we, even though I don't have a specific answer to this question, the more we look at the biosphere and the land surface, or in this case, the ocean surface, coupling with the atmosphere, the more we find that everything is in fact connected in a way that is maybe more profound and more and less intuitive, at least in a linear sense, than I think we might have imagined. So it's certainly possible. I just don't know if anybody's really looked at it.
Yeah, I have no idea if the albedo changes when the kelp forests disappear. It's seems plausible, but I have not seen any data on that either. So Charles, that's an open question. Just in terms of the impact of the ocean generally, Glenn is asking if you have any comments on whether heat uptake by the oceans is dropping. Can you talk a little bit about how, I mean, is when the atmospheric temperature rises, does the ocean temperature rise directly correlated? Is there any, what is the interplay between those two?
Yeah, well, so as you know, well, maybe we can infer this from the rate of warming over oceans versus land. The oceans are warming, they're just warming more slowly. It doesn't actually mean they're taking up less energy. In fact, the oceans are taking up vastly more energy than is the atmosphere or the land surface. And it is precisely because of the water's exceptionally high capacity to absorb that energy that it is warming more slowly. It's actually not a reflection that is not absorbing as much of the heating. It's actually just a testament to the enormous thermal capacity of a column of water miles thick, covering 70% of the planet. Uh, the ocean is actually absorbing the vast majority of global warming. It's actually occurring in the ocean. So even though the actual time rate of change, so degrees of warming per decade or something in the ocean is lower, that actually represents a vastly greater amount of energy accumulation than a much faster rate of temperature increase of the atmosphere because the atmosphere is much easier to heat up. It doesn't take as much energy to do so. Um, the oceans really it's actually quite a fascinating physical oceanographic explanation as to how those oceans uptake heat, and it has to do with essentially the deep ocean overturning circulation. If you've ever heard about the North Atlantic overturning or the South Atlantic overturning, it's essentially this three-dimensional circulation in the ocean where warm ocean waters in some parts of the surface ocean essentially deep dive down to the bottom of the ocean and then go down to the other hemisphere at the bottom of the ocean in currents that take decades to reach the other side of the planet. It's really just this incredible engine. And that's how heat and energy gets subducted into the deep ocean. So it essentially it warms by conduction near the surface. And conduction, if you know anything about heat transfer, is not super efficient, but if you do it 24 hours a day for decades, it does eventually happen. You exchange that heat between the warming atmosphere and the warming ocean. And you also change through warming the Earth the amount of solar energy that's remaining in the Earth system, and so you actually increase the amount of downwelling infrared radiation that gets absorbed directly. So there is also increased radiative heat transfer between the atmosphere and the ocean. So the ocean warms through several different processes. It moves all that excess heat around in this three-dimensional circulation. Interestingly, we're headed for what looks like it could be a very large El Nino event. And El Nino is the periodic warming of the eastern tropical Pacific Ocean. El Nino is nature's way of releasing excess heat from the ocean semi-periodically. It's kind of like you imagine you pull a spring back further and further and further, equivalent to the greater and greater accumulation of heat in the global tropical oceans. Eventually, you pull it far back enough and that it really wants to spring back in the opposite direction. That is what El Nino does, is it's that spring back. It's the ocean releasing a lot of its energy into the atmosphere, which is why we're very likely to have a record warm planetary year in 2027. Because if we do have a significant El Nino event this year, the deeper oceans release a lot of that subducted heat into the atmosphere and it lingers. It kind of looks like that's why global warming is a stair step, by the way. It looks like that every time we have a big El Nino event, it kind of permanently raises our new baseline. Then we kind of have this neutral period in between. The energy gets subducted into the ocean. We have lots of La Nina, and then it all comes out at once. And we dip a little bit after the El Nino, but we don't go back as down to the level where we started anymore. Whereas in a natural, unwarming climate, you would actually see a warming and a cooling, as has been said, roughly of similar magnitudes. But now we just see a warming and then a smaller cooling and then a bigger warming and then a smaller cooling. That's kind of how it's been working.
Which is kind of a bummer. Okay, I know we are at time, but I can't resist the opportunity to ask one last question. So I promise 2 more minutes. Talk to us about atmospheric engineering. Do you think it's worth pursuing, these ideas of spraying particles in the upper atmosphere to try to geoengineer our atmosphere to hold less gas or reflect more light or any of those ideas?
Well, so I am unaware of any extant or proposed technology that would actually do this by reducing the amount of greenhouse gases in the atmosphere. If there were such a technology, I would be more in favor of it than what is actually being proposed, which is mainly to inject essentially aerosols into the atmosphere to dim the sun, essentially to make the sunlight less intense so that yes, the global warming is still there and we're ignoring it, but there's less sunlight coming in to heat up the earth, and so therefore you have the heating and then you induce this cooling effect and you're just sort of juxtaposing them both and you have a very different earth actually in that world. And I think on the one hand, I mean, I have no doubt that we could cool the earth through solar radiation management. I'm sure it could be done. I mean, the macro science on it is fairly straightforward. The problem is we really don't understand the details, and the details are like, do we accidentally shut off the South Asian monsoon, or do we accidentally not allow enough photosynthetically active radiation through the Earth's atmosphere for plants to grow in the way that we're used to? Or is there a problem with phytoplankton? Or also doesn't solve things like ocean acidification because the CO2 levels just keep going up and up and up, and then we have an acidifying ocean. So the answer is, would it cool the Earth? Yes, I think it probably would. And the question is, at what cost? And I think we're at a point, it's a really complicated and controversial topic. I think we're at a point where there's a lot of people who are overconfident that we understand the side effects. I am not confident we have the scientific understanding that's adequate to understand what it would do in addition to cooling the Earth, which I'm quite convinced that it would do. But some of those other consequences could be really bad. The other thing is that we would have to constantly do that, maintain it using a fleet of air tankers constantly spraying the upper atmosphere, essentially every month forever, for the rest of not just our lives, but future generations as well. And if we're ever interrupted for more than a few months, say during a pandemic or a expanding regional or global war, we would instantly experience those decades of global warming over just a few months to a year. We would just have this just explosive warming if it were ever interrupted. So, rather reassuringly called termination shock by those who have studied it. So, I I think it's something that it's definitely something that someone's going to try to do someday. Um, and so we need to understand it. We do need to research this, not because I think it's a good idea, and not because it's a use. Could it be a useful band-aid in a limited circumstances under some hypothetical future? I think that's a possibility, but I think we need to understand it a lot better than we currently do, and we need to have a much better plan for actually still solving the underlying problem of increasing greenhouse gases. Because if we don't actually solve that problem, then we actually just keep making the underlying issue worse. So my general answer is we should probably study it so we understand how it would work And what's going to happen if someone geopolitically tries to do this unilaterally at some point in the not too distant future? But I don't think we should actually be doing it, essentially, is my answer right now. Not because it wouldn't cool the earth, but because it would, and it would also do some other things that we don't really know.
Thank you for that very rational explanation and answer. I appreciate it. All right, we have kept you long enough. I would like everyone to take a moment to unmute yourselves and give our speaker a big round of applause and thanks. We really appreciate your being here tonight.
Thank you. We
Thanks a
so
bunch.